Have you ever wondered how your car radio tunes to one station while filtering out all the others? Or how a speaker separates the deep thump of a bass drum from the sharp crash of a cymbal? Often, the answer is a simple trio with powerful behavior: a resistor, an inductor, and a capacitor. Not digital magic, but an elegant dance of energy. Together they form an RLC circuit. One acts like a brake, dissipating energy as heat. Another resists sudden changes in current. The third stores energy and releases it in a rush. They can store, release, exchange energy, and tune to a specific frequency. We will build intuition with simple visuals and analogies, not dense math. These circuits are a foundation of modern electronics all around us. Their principles echo in pendulums, guitar strings, and car suspensions. Let's pull back the curtain on this unseen orchestra. Let's begin with the simplest, the resistor. A resistor resists the flow of electric current. Like water through sand, current still passes, but less easily. It limits current for a given voltage. This opposition is resistance, measured in ohms. Energy isn't lost. The resistor turns it into heat. That warmth from chargers is resistors at work. In an RLC circuit, the resistor removes energy and provides damping. It makes oscillations die down. Think of it as friction that bleeds energy away. The resistor provides controlled loss and stability. Without it, ringing could go on. With it, the sound fades. Straightforward, predictable, and essential. Now, the inductor. Often a wire coil, sometimes wound on iron or ferrite cores. It doesn't resist steady DC, but it opposes any change in current. Current creates a magnetic field that stores energy. Like momentum in a flywheel, hard to start, hard to stop. Increase current, it pushes back. Decrease it, the field keeps current flowing. This property is inductance, measured in henries. Its opposition grows with how fast current changes. High-frequency AC meets a roadblock. Steady DC passes easily. In the swing analogy, the inductor is the mass, the keeper of momentum. By storing energy in a magnetic field and resisting change, the inductor shapes the circuit's dynamics. Finally, the capacitor. Two plates separated by a dielectric store energy in an electric field. Think of it as a very fast-charging battery. Apply voltage, charge separates, and the field holds energy. It opposes changes in voltage, slowing sudden rises. When voltage dips, it releases charge to hold it up, like a flexible diaphragm absorbing and returning pressure. This ability is capacitance, measured in farads. For steady DC, it becomes an open circuit once charged. For high-frequency AC, it continuously charges and discharges, offering little opposition. Inductor fights changes in current. Capacitor fights changes in voltage. It stores potential energy in the field, making it the perfect partner for the inductor. Now, what happens when we connect R, L, and C in series or in parallel? Resistor, inductor, capacitor. Arrangement dramatically changes behavior. In series, all share the same current. Voltages differ per component, but sum to the total. Resistor voltage aligns with current. Inductor leads, capacitor lags. This push and pull creates the interesting behavior. In parallel, all share the same voltage. Currents split among branches and add back together. Inductor current lags, capacitor current leads, resistor current stays in phase. Branch currents can partially cancel, unique to parallel RLC. Know what is shared, current in series, voltage in parallel, to predict behavior. Inductor stores magnetic energy and resists current change. Capacitor stores electric energy and resists voltage change. Across frequency, their opposites suggest a balance point. That balance point is resonance. At resonance, L and C exchange energy efficiently. Magnetic field collapses into capacitor charge, then the electric field returns current to rebuild the magnetic field. Their reactances are equal and opposite, so they cancel. In series RLC, only R remains to limit current. Impedance hits a minimum and current peaks at the resonant frequency. Like pushing a swing at just the right moment, each push adds up. Tuning a radio varies capacitance, shifts the resonant peak, and locks onto one station while others fade. The total opposition in AC is impedance, Z. It includes resistance and frequency-dependent reactance from L and C, measured in ohms. Inductive reactance grows with frequency. Capacitive reactance falls. Impedance combines R with the net reactance. Phase describes timing between voltage and current. With only R, they are in phase. L lags current. C leads current. The offset is the phase angle. Above resonance, behavior is inductive and current lags. Below, it's capacitive and current leads. At resonance, lead and lag cancel, and the circuit behaves purely resistive. Voltage and current resynchronize. Phase angle returns to zero. Switch an RLC on or change its input and it doesn't settle instantly. It first exhibits a transient response, its natural reaction. Like a bell's initial clash before a clear ring. Oscillations decay because the resistor dissipates energy as heat. Low R rings a long time. High R crawls without oscillation. Critical damping is the fastest without overshoot. After transients fade, the steady-state response remains. With a sine input, voltages and currents settle to that same frequency. Transients reveal switch-on behavior. Steady state shows filtering performance. Damping from R bridges transients into steady state. In AM/FM radios, a variable capacitor tunes the RLC to a station's frequency. Matching resonance amplifies one channel while others are rejected. The same resonance principle underpins wireless communication. In audio, crossovers route bass via inductors and treble via capacitors. Each driver plays only what it's built for. In power electronics, RLC filters smooth ripples and noise. RLCs form low-pass, high-pass, and band-pass filters. They control how systems respond to different frequencies. Think of an electrical swing. L and C trade energy. R adds friction, and component values set the rhythm that powers modern electronics.